Hi class, we are on to the next section in chapter 4, chapter 4.7. Today we're going to talk about derivatives of logarithmic and inverse trig functions. So it's really a way for us to take the derivative of any sort of generalized inverse function, more specifically the trig inverse functions. We're also going to go over what is called logarithmic differentiation, which is really just another approach to taking derivatives. Okay, so we know that if we have an inverse function, that if I compose the function with its inverse in any order, I will get out just my original input, right? So if I plug f inverse into f, then I get x. If I plug f into f inverse, I will also just get out x, right? So if we are using our idea of a plane trip, right? If I take a plane trip from San Francisco to New York, my inverse function takes me from New York back to San Francisco, and I just end up right where I started at, right? So taking, plugging the inverse function into its original function or vice versa just leaves us with the input value, okay? So what we're going to do here is we're going to take this fact and we're going to differentiate both sides. Now, I don't know what my function is. I don't know what f is. I don't know what f inverse is. I obviously don't know what f inverse is because I don't know what f is. So when I differentiate both sides, I have to differentiate implicitly, right? Which is why this section comes after implicit differentiation. So if I differentiate both sides, x goes to 1. I don't know what these functions are, so I have to take the derivative. I'm using just the derivative notation. So now when I start to actually evaluate this, I have a function inside of a function. So I'm going to use my chain rule in order to do this. So I will have the derivative of f with an input of f inverse, and I'll multiply that times the derivative of f inverse, which I don't know what this looks like, right? But my whole goal here is to figure out derivatives of inverse functions. Okay, so what I'm going to do is I'm going to isolate the derivative of this inverse function. So I'm going to divide both sides by this f prime of f inverse of x. So the derivative of any inverse function is 1 over the inverse function being plugged into the derivative of my original f function. So now we have a formula for how to find the derivative of an inverse. So this will be useful, again, more so for trig functions rather than, I don't know, trying to find the derivative of well, obviously we can do this for natural log too, since e to the x and natural log are inverse functions. We haven't yet talked about how to take the derivative of a logarithmic function. That's the only function we haven't done yet. And so using this fact is how we'll find derivatives of logarithms. Okay. All right. So let's start off with something we're familiar with, cosine inverse, because we know about the cosine function. We know what the derivative of cosine is, right? So remember what this rule is. It's 1 over the derivative of my function with its inverse being plugged in. So I know what the derivative of cosine is, right? So the function I'm using is f, right? An original function, plugging that in. So the way that we're going to do this is we're going to set up the exact same way. Literally the exact same way. I know that if I plug cosine inverse into cosine, I will get out x. So that's what I'm going to do. I'm going to start off with literally the exact same thing we did up here. Plugging the inverse, the one that I'm interested in, into the original function so that it and its inverse cancels out. And then I'm going to differentiate both sides. So when I differentiate both sides, I will differentiate this implicitly, and this will go to 1. It'll literally just follow the exact same formula we did, except with the generic function, we'll be using the actual cosine function. So differentiating both sides, I will have x will go to 1. This is going to be negative sine with cosine inverse plugged in times the derivative of cosine inverse. Okay, I want to isolate cosine inverse, so I'll divide both sides by negative sine cosine inverse. Okay, and now you might say, oh, that was pretty easy, but we're not done yet. This is a terrible answer, right? If I try to use this, if I wanted to, I don't know, find the derivative at x equals 3, for instance, that's a terrible thing to try to use here function-wise. So what we're going to do is we are going to simplify this by using a triangle, okay? More so by using some relationships between sine and cosine, okay? So again, the formula we have here matches perfectly with what we have for this formula, right? Since the derivative of f, which was originally cosine, is negative sine of x. So again, here it's very important that we make a substitution for sine of x in terms of cosine so that we can use this property that cosine of cosine inverse of x equals x. So we're going to figure out something to make this a little bit easier to look at. Okay, so we have a relationship between sine and cosine. Okay, so again, I want to turn sine into cosine so that this bottom notation here turns into just something in terms of x. So if I'm looking at sine and cosine, the easiest relationship that I have is sine squared plus cosine squared equals 1. So what I'm going to do is I'm going to solve for sine into terms of cosine. So if I solve for sine, it'll be 1 minus cosine squared, square root both sides, and I'll have square root of 1 minus cosine squared of x. So taking my derivative that I just found, okay, and using this form for cosine, what I'm going to do is I will plug in cosine inverse into my sine. So what that means is for this right hand side, I'll have 1 minus cosine squared of cosine inverse of x. Okay. So when I plug that in, this is what it looks like, 1 minus cosine squared, and I'm plugging in my cosine inverse of x into this equation. So now what I get to do is I need to take this and I need to just separate it into its two parts. Okay, you don't always have to do that, but for this example, I want to show to you exactly what's happening here, right? Because this is cosine of cosine inverse of x times cosine of cosine inverse of x, right? It's being squared, so there's two of them being multiplied. I know that cosine of cosine inverse is x. Okay, so I can replace each time I see this now with x. Right, so this is 1 minus x times x, or 1 minus x squared. So instead of having this crazy looking answer here of 1 over negative sine of cosine inverse of x, which is going to be very, very difficult to work with, we've simplified it now down into a function of x. So negative 1 over square root 1 minus x squared. Okay. So instead of going through the derivations for the other trig derivatives, the other trig inverse derivatives, I'm just going to go ahead and give them to you because their derivations are literally exactly the same. When you get to tangent and cotangent and things like that, instead of using sine squared, cosine squared, you'll use the Pythagorean identities for the tangent and secant functions, which is, you can derive from here just by dividing everything by cosine squared, for instance. So if I divide everything by cosine squared, this turns into tangent. Let's come back up here. This would turn into tangent squared plus 1 equals, this would be 1 over cosine, so this would be secant squared, right? So you would just use that relationship if I was trying to find the derivative of, let's say, tangent inverse. Okay, that's the relationship I would use instead. So some more derivatives. So whenever I'm taking the inverse of any function, as you saw, this is the formula that I use. Okay, if I have to substitute into this function and simplify further, then that's what I do, like I just did. I didn't show you for natural log. We'll just go ahead and talk about what that solution is. Here it's just going to be 1 over x. Okay. For sine inverse, so getting into the trig functions, we're going to have 1 over square root 1 minus x squared. So same thing for cosine inverse, but positive. For cosine inverse, we derive that together. So it's the same thing, but negative. Tangent is going to be 1 over 1 plus x squared. Cosecant inverse is going to be negative 1 over x square root x squared minus 1. Secant inverse will be same thing, but positive. And the only one we're missing at this point is cotangent inverse, which is 1 over 1 plus x squared, but negative. So if you haven't seen the relationship here, they pretty much go together, right? Sine and cosine go together, but they're opposite signs. Tangent and cotangent go together, but they're opposite signs. Cosecant and secant go together, but they're opposite signs. Okay. So let's do some more examples with inverse functions. So let's say I wanted to differentiate tan inverse of x squared. So now that I have the formula ready for me, I could just use this formula. I can go straight to this formula, right? I don't have to use the derivation method like we did before, although it would be helpful to do so. We can go straight to it. Here, obviously, I have to use the chain rule, right? Because I have a function inside of a function. So I'm going to differentiate the outer function where I have an input of x squared, and then I multiply that times the derivative of the inside function. So for a tangent, we have 1 over x squared. So into that, I have to plug in x squared. So this will be 1 over 1 plus x to the 4th, or x squared squared. And then I will multiply that times the inner function. Okay. So I'm taking the derivative of the outside function, where I still have this as the input, and I multiply that times 2x because of the chain rule. So what does that look like? I have 1 over 1 plus x squared being squared because my input I'm still plugging this in to the derivative of the outside function, and then I multiply that times with 2x. So when I simplify this, I get 2x over 1 plus x to the 4th. Okay. Now, very, very closely related to what I had before. For inverse functions, we don't put the 2 next to the trig function because it's hard to tell what's going on here. Unless I wrote arctan squared, then it's very clear that I'm taking tan inverse and squaring it. Why don't you go ahead and take the pause I'm going to give you in just a moment to try and differentiate this yourself. Okay, so hopefully you try this out and you're coming back now to check your work. So here's just the standard chain rule, right? So the outside function in this case is 2. So I have 2 times tan inverse of x times the derivative of tan inverse. So this should say 2 tan inverse x, and I'll multiply that times 1 over 1 plus x squared. Okay, the derivative of tan inverse. So I got 2 tan inverse x on top over 1 plus x squared. Can't really take this down any further than this either. So this is as far as we can simplify. Okay, same thing here. We're going to differentiate f of x is natural log of 1 minus cosine x over 1 plus cosine x to the 4th power. So this 4th power is not to what's on the inside, it's the whole natural log. Okay, it's very important that you're familiar with what the powers are being applied to. If I wanted to apply it to the inside, I would have another set of parentheses with the 4 across those, and then the natural log outer parentheses. So very important that you can differentiate the difference. You should go ahead and do the same thing. I'm going to pause for a second so you can pause this video, and then you can try to do the work on your own and then check your work against what we have here together. Okay, so hopefully you went ahead and tried to do this on your own. And let's see what we get when we try to differentiate this. So the outside function is this 4th power here, and then we have another outside function of natural log, and then the innermost function is this quotient function that we have here. So we'll be doing the quotient rule as well. So I'm not going to use the UVW method. I really only talk about that when I first go over the chain rule. After we've done chain rule quite a bit, we just kind of go. Okay, so we're going to have 4 times natural log of 1 minus cosine x over 1 plus cosine x. All of that to the 3rd power, so that's just the outside function. Okay. Then the inside function is my natural log. So I'm going to have 1 over 1 minus cosine x over 1 plus cosine x. Okay. So I'm going to keep using this notation here. So let's go to the next line. So for natural log, and then everything on the inside to the 3rd power, the derivative of this is 1 over. So I also then have to take the derivative of what's going on the inside. So the derivative of 1 minus cosine of x, 1 plus cosine x. Okay, so here I'm kind of going in pieces. So as I move forward now, I'm going to take this and I'm going to simplify it just a little bit. So the only thing I can really simplify is this. If if I have 1 over a fraction, that means I can really just put this as the reciprocal of what I have. So on this next line, I'm going to simplify this term to be just 1 plus cosine x over 1 minus cosine x, and I'm going to actually do the quotient rule here. So then I'll have my derivative completely derived, right? And then I just have to do some simplifications after that point. So for natural log with the inside, everything to the third power, so that has been staying the same the whole time. I took this and I simplified it. And then now I have to multiply each of these now by this quotient rule. So differentiate the first term, and I'm going to have sine of x because 1 goes away. Cosine changes to sine and it changes sign, so this negative becomes positive. So I have sine times 1 plus cosine x. I'm going to do the whole thing. Okay, I'm going to subtract from that. 1 minus cosine x staying the same, and this turns into a negative sine of x. And I divide, sorry, I was going to say differentiate. I divide the whole thing by 1 plus cosine of x, and I square that value. Okay. Now from here, I can pull out a common sign if I want to. That's really the only thing I have in common. I'd probably distribute this negative first. So it's 1 plus cosine plus 1 minus cosine, and have the sign on the outside. Okay, so far here I haven't been able to do anything. Here I can start to simplify. So when I pull out my sign, what I'm going to be left with, 1 plus 1, because this negative gets distributed. So I have a 1 plus 1, and then I have a cosine. This will be a plus, a negative cosine, so the cosine goes away. So I just get my sign that I pulled out times a value of 2, right? 1 plus 1 is 2. So I have 2 sine over this 1 plus cosine of x, this whole thing being squared. Then notice here I have 1 on top and 1 on the bottom, so I actually get to cancel this 1 on top. So I will have my 4 natural log, this whole thing of 3. When I simplify this, I'll have my 2 sine of x, I have 1 minus cosine, and I'll have 1 plus cosine, because this 2 will cancel with the 1 here. So I'll actually have a difference of squares in the denominator. Okay. And it looks like I took this 4 and I moved it from being in the front to moving it up here to play around with these trig functions as well. Right? So that canceled away. The 4 I just brought over here because this is the stuff that's being simplified, so I'm leaving this natural log thing over here by itself. Again, let's go back one slide. So 4 is coming over here. This 1 plus cosine is canceling with the extra 1 that I have here. So I got a 4 on top, 2 sine x, and then on the bottom I have a difference of terms, right? Difference of squares, because I have a 1 minus cosine and a 1 plus cosine left over. So when I actually multiply this out, I will have 1 minus cosine squared. Okay, and I have an 8 here. And I know 1 minus cosine squared is the same thing as sine squared. So really what I get is 8 sine of x, natural log of this whole thing here. Okay. Sorry, sine of x on the bottom because it cancels. So I can rewrite this if I want to as cosecant of x. So then it flows a little bit nicer. I got 8 cosecant x, natural log of 1 minus cosine of x over 1 plus cosine of x, that whole thing being cubed. So again, the cube is going to the natural log. It is not this inside part that is being cubed. All right. So that's the simplified form. Okay, so again, when you compare it to its non-simplified form, there's a lot going on here. And then it simplifies down to really just 2 factors, right? Or 3 factors if you include this 8. Even more factors if you include each of these terms of this cube being a factor as well. So now we're going to talk about logarithmic differentiation. So logarithmic differentiation is not just for logs. It's really a way of differentiating really any function. Okay, especially now that we have all of our rules out there. We will go over some new rules in the next section, but that's because we're going to talk about some new functions, period. So we have to talk about how to differentiate those. But as of right now, everything that you've seen in your math career up to this point, most likely, we've covered. So we know how to differentiate pretty much anything up to this point. Again, in the next section, we're going to introduce some new functions, and we're going to talk about their derivatives. So we're still going to use the methods that we have at this point. So you know how to differentiate everything after this point. So this method we're going to go over now just helps us to have a little bit more versatility and adaptability when we want to differentiate things. So we can use this for easy functions, and we can use it for even more difficult functions. So again, it's called a logarithmic differentiation. The steps are pretty easy, actually. Really easy if you're really comfortable with logarithms and exponents. So the first thing we're going to do is we're going to take our function and we're going to set it equal to y. Okay, so I know a lot of times we'll say f of x equals this thing. So what we'll do is instead of f of x, we'll write y equals whatever we have. If our function is already y equals, which I don't have anywhere here, then we're already set. Okay, so if not, we'll just replace f of x with y. Right, so y and f of x are always equal at this point. What we'll do is we'll take the natural log of both sides and simplify if need be, and then after that we will take the derivative of both sides. Okay, so I'll take natural log of y, I'll take natural log of my right hand side, I'm sorry. If I have to simplify, then I will, and then I'm going to differentiate both sides. So I will focus on what's going on here on the left. Right, so when I take that derivative, I get 1 over y times y prime. And for my function here, I will get 1 over f of x times f prime of x. Okay, so again, remember, we're doing this implicitly. I don't know, I do know what y is, but I don't know what it is, right? I'm assuming I don't, because the variable I'm taking the derivative with respect to is with respect to x. So y is a function of x, so we use implicit differentiation. F of x, we already know that this is what it's going to look like when I have natural log of a function. So from here, I just solve for y by multiplying by y, okay? And remember, y and f are the same thing. So if I multiply by y, this turns into y prime. This does not turn into y over f of x is f prime of x. It ends up being y prime equals f prime of x, which is true. The derivative equals the derivative. It's just the manner in which we do it allows us to solve what I have. So these things are the same, so they cancel out, and I just have my derivative. So let's do an example. Let's do something difficult. F of x is x cubed over e to the x squared logarithmically. So this isn't actually difficult. This is something that we can do now using a regular quotient rule, right? Using the quotient rule, I know I'll get 3x squared times ex squared minus x cubed times 2x ex squared over ex squared squared, right? So I can just look at this. Hopefully you can follow that, but you know, this isn't actually too difficult to use. It's the quotient rule and the chain rule because of this bottom function, but we've been doing this quite a bit, so we know how to do this. So instead of doing it through the standard quotient rule method, we're going to use it, we're going to differentiate it logarithmically. So we're going to set it equal to y, okay? I'm going to take the natural log of both sides. I'm going to use my rules of logarithms here, and I will rewrite this as natural log of x cubed minus natural log of e to the x squared. This can be simplified, this cannot be simplified, but this actually turns into x squared because I have natural log of e. The power rule says that this comes down. Okay, so it looks a little bit nicer maybe than, you know, what it did before. Now what I'm going to do is I'm going to differentiate everything. Okay, so this is going to turn into 1 over y times y prime. This is going to be 1 over x cubed times the derivative of x cubed, so times 3x squared. And this turns into 2x. Okay, so here we'll just go with the notation. I differentiate the left side, differentiate the right side. I get 1 over y times y prime. This is 1 over x cubed times the derivative of x cubed, which is 3x squared. And this turns into 2x. Now I multiply everything times y because I need to get y prime alone. Okay. And then I just replace y with what y was. Y was my function. So I'm going to replace y with x cubed over ex squared. Okay. From here, I'm just going to simplify. So here the 2x cubes cancel. So I'll have 3x squared over ax squared. And then I will have 2x to the 4th over ax squared. Right? Notice now I have a common denominator. So instead of trying to like pull it back out, which would undo what I did, I'll just combine them over their common denominator. So I will have 3x squared minus 2x to the 4th over ex squared. Here I can pull out the common x squared, and this is my answer. Okay. Now if I were to have differentiated this using the quotient rule, I would have gotten the exact same thing. Okay. Right. You can verify this on your own if you want, but we'll verify it here as well. So maybe do this on your own and then double check that you got the same thing, and we'll go over it together right now. So again, this is my answer: x squared times 3 minus 2x squared over e to the x squared. Differentiating logarithmically, okay, using the quotient rule, this is what I would get. So again, x cubed over ax squared. So differentiate, leave alone, differentiate over the bottom function squared, and then start to simplify, right? So I can pull out an ex squared from everywhere. Okay. And then here I can pull out my x squared, and I have the same thing. So you can definitely argue that this was a lot less work, although maybe you're not super comfortable with the quotient rule. And so differentiating logarithmically maybe makes more sense to you because you're just using rules of algebra, right? The only derivative you had to do was natural log. And if you're okay with natural log, taking the derivative of natural log, then it'll always be pretty easy. But you will always come up with the same answer. So here's one where you can choose either method. Obviously this was a lot longer than the 3 steps here. However, there's going to be times where we don't have any other method except for logarithmic differentiation, like in the next example, okay? X to the 2x. So now maybe you're saying, well, I'll just use the chain rule, okay? I guess you could probably use the chain rule. You might be able to use the chain rule here. It's odd because I have my variable in 2 places rather than just 1, right? So we can't use the product rule because I can't really separate this out. We're going to differentiate logarithmically. So I'm going to take the natural log of both sides. Taking the natural log here, the power rule allows me to bring the 2x down. Okay. Now I take the actual derivative. So I will have to use the product rule here, but this will be 1 over y prime, right? This, I use the product rule, so it turns into 2 times the regular function plus my regular function times 1 over x from the natural log, and I multiply that times x to the 2x. So now when I simplify, I will have just a 2 here, okay? And I can pull out a common 2 if I want to, and my answer turns into 2 natural log of x plus 1 times x to the 2x. Now if we had used the chain rule, we would not have gotten this as an answer, right? There's no way we'd have got it. If we said it's x to the u, that wouldn't work because we still have this variable of x here. We would not have gotten this natural log out. So here we have to use the logarithmic rule. Okay, and that's how that works.